Today we're going to talk about QuickSort. Why this algorithm is called quick? Because it's very quick. Yeah, so let's talk about it. So, the main principle of this algorithm is pretty similar to the merge algorithm. We need to we need to separate some elements of this array and do it recursively. So the main technique of this algorithm is a partition. So we need to find our so-called pivot, like the pivot element, and we can define it in any way. Like we can say our pivot is our first element, or our last element, or like any random element. Let's imagine that our pivot is all the time is the first element. So this is our pivot. Then we need to define our first element and last element except pivot. It's like element next to pivot, I, and the last element, J. So now we need to check, first of all, we need to check every element here if this element is less than our pivot. So for example, we're checking 7 is bigger than pivot. So we stopping here. Next, element J. 9 is greater than pivot, so we move on. 10 is greater than pivot, we move on. Let's do something like this. So 3 less than pivot, so we moving our J here. And now we need to swap those elements. So 3 will be here. And 7 will be here. Why we are doing this? Our purpose is to create such array where our pivot will be, we need to find place to our pivot. And when we find place for pivot, all the elements left to pivot need to be less than pivot. And all the elements that on the right side of pivot must to be bigger than pivot. So now we are moving like on the left side and trying to move all elements that bigger than pivot to the right side. So we stopped here. So our I was here and our J was here. We are continuing our actions. So next element, I is less than pivot, so we move on. 4 is less than pivot, we move on. 8 is bigger, so we are stopping our I here. Next, our J stops here. We move on. 12 bigger than pivot. Move on. 13 bigger than pivot. 8 bigger than pivot. 4 is less than pivot. So our j is here. If our I is bigger than j, it means that we need to stop those operations of moving I and j and swap pivot with j. Like this is a final operation of the partition method. So at the end of partition, we have 4. So what we have now is that our pivot now here, and all elements that on the left side from our pivot is less than pivot, and all elements on the right side of our pivot is more than pivot. They are not sorted yet, but the main point is that after our partition operation, we need to have such array. Is it clear? So now we started our recursive operation. So we doing the same partition, but now with 2 arrays that contain elements that on the left and on the right side of the pivot. So now our pivot is 4 in this array, and here our pivot is 8, right? So now let's do the partition in this array. So our I now is here, j is here. Is this clear? Okay. We check it. Our I element is less than pivot, then it means that we are moving I here. This element is less than pivot, so we are moving our I like out the boundaries. And we can do this actually. We have to check if we are not out the boundaries. So we are stopping here, and I is our last element. So now we're doing our actions with j. So 1 is less than pivot, so we are moving j backwards. 3 is less than pivot, so we are moving it here. And here we need to stop because j is equal to pivot. And now, what's happening now? Let me think.
But before we moved j when it was greater, when our j was greater, right?
Yeah.
Like before, like in the beginning, we moved j when the number was greater than pivot. Maybe we don't move.
Yeah. Yeah, you're right. So j is still here, right? Because 1 is less than pivot. So, and we stop here because e equal j. So we don't start the next iteration like here, for example. And now we need to, what we need to do?
Swap p and I.
P and j.
And j, yeah.
Yeah, because we stopped this operation moving I and j because they're equal now, and we need to do our final operation in the partition method. It's swap pivot and j. So what we have now is this, and our pivot now here. So everything that less than pivot here, and we don't have anything more than pivot, right? So now we do recursive operation with this part. We can see that it's already sorted, but computer can see it. So we need to do this operation once more. So now 1 is our pivot, E and J is our this element, and we check it. Okay, 3 is more than I, so we want to move I forward, but we can because it's boundary. And J, 3 is more than 1, so we need to move J here. We can see that I is more than J. It means that this operation of moving and swapping I and J is over, and we need to swap P and pivot and J. This is the same element, so we leave it as is. So now our pivot is 1. Everything that greater than 1 is like greater than 1. So like this part is over, and we can see that our like if we will recursively go back in our main array, we can see that this part is already sorted. And now we can do the same thing with right part, and I want someone to help me. Yeah, Roshan.
Okay, so we have pivot A and I is 13.
Yeah.
And J was
Yeah.
we compare I with pivot.
Yeah.
And we don't swap them because I is bigger than.
Yeah, we don't swap them.
And we move I to +1.
Mm-hmm. So, when we check those elements that like on the I side, we need to check if they are less than pivot, because everything that left from the pivot must to be less than pivot. So 13 is greater than pivot. So we need to stop here to swap this element with some elements that less than pivot from the right side.
Pivot is P, yes.
Pivot is P, and it's our first element when we start this operation. So we're saying that our I is this element because it's greater than pivot. Then we move to the J. So maybe try this part. So 9 is what?
Is what I compared.
With pivot.
Okay, it's bigger than it. And
Yeah. So what we're doing with J?
Nothing, I guess.
No. We moving here because we want every element that bigger than pivot is like after our operation was on the right side of pivot, and now this on the right side. So we leave it here. Okay, so 7.
It's less than 8 and J swap.
Yeah, so we saying 7 is less than 8, less than our pivot. And in the I section, we have elements that bigger than pivot, and we want to move it in the right position. So we're swapping those two elements. Is like,
It's mind-blowing.
yeah. So let me write this, and maybe we will.
That mind-blowing stuff is quick and memory efficient.
So now, what we have now is here on the left side, after pivot, we have elements that less than pivot. This is our goal. And here now, everything, including j and after j index, we have elements that greater than pivot. And this is also our goal. And if we will come back to the previous operation, you can see that everything we done, we had our only purpose to move everything that less than pivot in the left side, everything that greater in the right side, and move pivot between those parts. So now we're doing the same operation because it's like the same method. It will be a recursive algorithm. So, Arsene, let's move on. Our I now, this element, we're moving it right? So, what we're doing here?
It's bigger than 8, but it should be less than 8.
Yeah,
So we swap them.
no,
Remove I, for example.
no.
J.
We leave I here because if we want to swap this element, we need to leave it before we will be able to swap it with j element. Okay? So we leave it here. We stop this operation. We move to the j. So j will move here. What can you see about this element?
J is bigger than 8, and it should be bigger than 8.
Yeah, so
Maybe break once again.
what?
Break is
No, if element in its place, we need to move j to find elements that not in the place. So when you do these operations, if element in the right place, you leave it there and move to the next one to find elements that not in the right place to swap it. So now j here, we check if I bigger than j, it's mean we're done with this operation of moving and swapping. And what we do after this? Yeah, but one action, and Yegor said about this action twice, I think. So after we swapped all elements except pivot, we need to move pivot in some place. In what place? Not between I and j, but yeah, swap p and j. And it may look confusing, but it makes sense because I is bigger than p. This is our umova. Yeah, that I stops when this element is bigger than pivot, and we don't want elements that bigger than pivot move to the place of pivot, because in such situation we will have the right configuration of our array. So we need to change j and pivot, because j is less than pivot. This is our condition, And we don't mind if it will be not sorted. We don't care. Our only goal in this operation, so every element larger than pivot need to be less than pivot. So what we have here, we can see that our pivot will be here now, and everything on the left side from the pivot is less, everything on the right side of the pivot is more. And now what we're doing, right part, yeah, because left part is just only one element. In the right part we have some elements.
How do we check if it's sorted or not?
What?
How do we check if left or right part is sorted or not?
We need to move to the moment when we have only one element in the array, because when we have one element in the array, it means it's sorted, right? So here you can see that we have two elements. We have our pivot. That means that we need to do the partition to the one element, and it's sorted. So we move on, move on, move on. But before this moment when we have one element, we like 100% we will have sorted array, because like we do this operation. Is this okay? Is this clear? Okay, who wants to help me with this part? Yeah.
All right, so let's take the first element as a pivot element.
Yeah.
And well, I is 13, J at 9.
Yeah. So pivot is the first element. It's for the guys on the video, and I is the next element from pivot, and J
Is the
last element.
So let's check. First of all, I is greater than pivot, so we're already there. Okay, J is less than pivot, and we're also already there, I think. It seems like. J is less.
Yeah. Why we not move I and J?
Because I needs to be greater. Like we need to find an element
Yeah.
that's greater than pivot, and it's already greater.
Mm-hmm.
J, we need to find an element that's less than pivot, and it's already less, so we're there.
Yeah. So basically,
And now it's swapping.
I element not in right place, and J element not in right place. So we stop here and
And swap them.
swap them. Okay. So what happened?
Okay. And now we have, I think, I at 9. Yeah. I first element.
No. After swap, we need to increment I and decrement J.
Okay, yeah,
So
we have,
not to.
yeah, like we have J at 9 then, and I at 13.
But your logic is correct, because like, for example, if I here, we do
Then
it.
we'll anyway go.
Yeah. So you're saying the right thing.
Like it's just
Yeah.
It's the next step. Okay.
Yeah, the same thing with J, right?
So, okay. We have I. Yeah. So J also like increments, and it's at 9. Yeah.
Yeah.
And now we have J less than I,
Mm-hmm.
and that's why we swap J and
Mhm.
P and J. Pivot and J. And now we have everything that's more to the left of the pivot, to the right of the pivot. Everything that's less to the left of the pivot.
Yeah, and on the left and on the right side we have only like one element. So if we will come back, 8 here, so we can show here our sorted array. It will be, let's do this. I don't know. here. So, what we have here? 1, 3, 4, 5, 7, 8, 9, 12, 13. We have sorted array. Is this clear? Maybe someone have questions about this algorithm. Yeah.
How did you swap invent 12?
And 9?
Okay, like this is the three last operations.
Everything here, right? So, our pivot is our first element. Our I is an element next to pivot. Our j is our last element. We checking. I element 13 is greater than 12. It means it's not in right place because it needs to be less, right? So we not moving our I, we leaving it in this position, right? Our j is less than 12, mean it's not in the right position because everything on the right side need to be greater than pivot. So we leave it here, and after this we need to swap those elements, swap I and j, and we have such configuration. And now, for example, our I is here. 9 less than pivot, so we move I here. 13 is greater than pivot, so we stop here. 13 is greater than pivot, and also it's our last element. We can move I further, so we stop here. Our j is 13. 13 greater than pivot, so we move it left. And 9 less than pivot, so we stop here. But I now greater than j, not the element but the index. And if I greater or equal to j, it means we need to stop our swapping operation and do one more swap. We need to swap pivot with j, and we do it here. So yeah. And after this, we could do another pivot with sub arrays, but we don't have any sub array greater than with one element. So we, like recursively, will come back at the start. Yeah. Okay. Okay. So the big O of this algorithm. What do you think? What will be the best scenario? Best.
Something like log.
Yeah.
So I guess either nlog n or log n.
Yeah. So best and average scenario is O log n, and you can find similarities with the merge sort, but we have one problem. The worst scenario of this algorithm is O n square.
If the pivot is chosen like absolutely wrong.
Yeah, if our array will be already sorted, our pi will always be at the left position. So we need to do this recursive operation n times. So the worst scenario is n square. But we can eliminate this problem just shuffling elements in the array before we will sort it. So, for example, yeah.
What if instead of shuffling, I just like choose any random pivot?
Yeah, for example, it's an option too.
Yeah, like why, like why do 10,000 operations to shuffle? It's you can just like do one constant random number generation call it.
Yeah, for example, it's a good option. You can and to not change the algorithm, you can find random element and swap it to the first one. So it will be the same but more stable. But another solution is to shuffle all the elements, so the possibility of the sorted array or partially sorted array will be very small.
Shuffle.
Shuffle mean like перемішати.
Ah,
Yeah.
So we use marriage sort methods and QuickSort.
No, no.
okay. And like, isn't shuffling also like time consuming?
Yeah, but it's what's the time complexity of shuffle
In which kind of list?
in every list? Time complexity is not related to the size of the list. Like n½ is the same as the n, it's linear progression. So yeah, shuffle is only O(n), so it's not a big deal.
Well,
Yeah, so even with the shuffle, QuickSort is faster than merge sort, just because you can do your tests with this. But I saw, maybe later I will show you this like comparison of merge sort and QuickSort and insertion sort. So the same, for example, for the 10 billion elements array, insertion sort will work for 300 years. Merge sort will work for 20 minutes, and QuickSort will work 12 minutes. So QuickSort will be faster. Even like we have the same time complexity for the average and for the best option, like n log n, but in practice, you will see in your project that QuickSort is much quicker, and that's why it's like industry standard, and even in Java, standard sorting that built in the Java is a QuickSort. So maybe you have questions? Yeah.
So time complexity is the same, but actual time is different.
Yeah, because like time complexity show us the like yeah.
Good and hard question.
Yeah, it's not easy to answer this question. But for example, n square is a worst scenario. So for example, if we have 100 elements, n square is 10,000 operations, right? But 9,000 operations is also n square, because n is 100, and 9,000 operation, it's much more than 100 operation. So 8,000 operations, it's also n square.
It's like it's not necessarily like the like the exact number.
Yeah.
It's like somewhere around n
Yeah.
squared and somewhere around n log n, for example. Okay.
Yeah, and also log n, we don't have the base of log. It may be 2, it may be 20. So it's about the prediction of прогресія, right?
How quick we will grow? How quick we will grow, depending of growing of number of elements. This is a big O is about that. So how we it is not about exact time.
So it's but more about speed, yeah?
This is more about how will we grow. So like Vlad already said that interesting example with his own maybe experiments. But yeah, this is the idea, and n log n will be even less than.
Okay, yeah, like
Yeah.
so
So
just like how do we like all like time complexity? Is it more about like the exact like time, or more is it more about like the approximate, or
So
it's more about like only the speed and
so you should understand. This is maybe a hard like.
like
This is hard conversation, but still very, 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 very important. So that's why you need to understand, like that example regarding that 10 billions elements. When we take insertion sort, and we have how 300 years.
Yeah.
So 300 years, or 20 minutes, or 12 minutes. Okay, you understand? This is one.
yeah, like
This is still less, but in general, this is one growing time, and this is absolutely years. This is absolutely something good because just remember mathematics. Remember this
yeah.
curve, how it goes. Regarding when we be here, you could imagine how many operations we need. But if we have this kind of curve, so that's why big O it is how to predict how we predicting time consumption of the algorithm in regard to growing count of elements. This is just
Okay, so
this
it's
is not just exact time. This is how we predict growth. So I could write wonderful algorithm. For example, I have in my scientific work I have algorithm of n in third power.
okay,
I run it on my graphs, and that's okay
And just
when we build some specific. But it will not survive
with
if I have millions of nodes, and this is just will not work, and I need to solve this task in another manner. So I need to some. So that's why it is so important to understand that bubble sort with n square is an insertion sort and so on. They so bad in comparison to n log n, because when we have our database is growing day by day, week by week, year by year, we still need to do that operations. And of course, now I'm ready to wait 2 minutes, but I'm not definitely ready to wait 300 years. And but I'm ready to wait 20 minutes or 12 minutes, and here I will choose what to do. So yeah, this is the difference you should understand in big O. How more time we need in the depending of how our data set
okay,
is
so
growing.
it's more about like approximate time predictions, yeah?
Yeah.
Not exactly, but somewhere around.
Yeah. Before we maybe other questions, and I propose maybe to make on the whiteboard one more example.
Yeah,
with
yeah.
help of
Mhm.
here, maybe call someone. Yeah, but if you have more questions, please ask the question.
Yeah.
What is the most efficient sorting method?
I don't know. Quick sort is pretty efficient. Maybe there are some other types that's more efficient.
And this big O is n power 3, so it is not possible to sort every time, not to sort, but to build something every time. Then what? We could find in other ways, think out of the box, yeah? We could think about in other ways how to keep maybe our data sorted. So, for example, I will not sort every time all the data set, but when my data set is growing, I will add elements in the correct position. Okay, we're thinking out of the box. So we're not sorting every time this element. I add an element and sort array again. Add an element, sort array again. And 300 years. So we could think, okay, maybe we could accomplish that sorted data set in another way. For example, we will insert our element in the right position in our data set. So we not only sort, but we create such data structures which allows us to put elements in the correct position. And this is exactly we will talk a little bit just briefly on the next week about trees, for example. This is another data structure. When we could perform sorting using trees, for example, when we add elements, we just put element in the right position. And talking about these binary search trees, there are red-black trees, and there are more and more data structures, how we could accomplish some tasks which we try to accomplish with basic algorithms, but maybe we, thinking out of the box, come to this task from another side, and we create something another, so we will not sort, but we will keep sorted data structures, for example. So this is just quick answer that the answer could be not only in the most efficient algorithm to do this, but maybe there are another ways to get the same results, but coming from another side. I don't know if you get what I mean, but something like that. Okay? Maybe other questions.
We need, on the first step, we need to create copy of first half and second half. Then we need to create copy of 1 quarter, second quarter, and so on and so on. So merge sort needs more memory to create those duplicates. And merge sort is efficient. Merge sort don't have such problem. In every case, merge sort will be n log n. It's not have problem with the worst scenario n square, but it needs more space. Yeah, so maybe someone have question. Okay, so let's do another run of our sort. So we have such an array. Andrei, can you help me?
Yeah.
So let's do the first run of the QuickSort. What we need to do for this?
So we have to compare 10 to 0.
No. First of all, we need to define pivot.
7.
Yeah. So then we need to define our initial I and j.
10 and 0.
So E is 10 and j is 0.
1.
Yeah. So what we need to do next?
We have to compare 10 and 1.
No. First of all, we need to compare not not I and j, but I and something else.
Pivot and I.
Yeah. So
But we don't have to solve because they are in the correct.
yeah. So I is greater than pivot, and on the left side, elements need to be less than pivot, right?
Yeah.
So if element I is greater than pivot, what we need to do with I? Not with element I.
I mean, we have to then compare I to J, or just check.
No. So what we need to do is if our element in the left side is greater than pivot, it means it's not in the right position, because we need on the left side only elements that less than pivot. So we are not moving I forward because we need to swap this element with some elements that will be on the right side. So you can imagine that we have two loop operations in this partition method. First loop operation is to find I element that we need to change, then find J element that we need to swap, then swap them, and like do it n times. So 10 not in right position. So we like breaking this loop operation and moving to the next loop operation. So what we're doing here?
Maybe we have to compare to, for example, 0.
No, we need to, like with this element, we need to compare it with pivot. So we compare 10 with pivot. 10 need to be less than pivot, so we move I. If this element greater than pivot, we stop. Here, another situation. If this element less than pivot, we stop. If it's greater than pivot, we like saying, you're in the right place, I can go now and find another element that's not in the right position. So, I is what?
I mean, do we have to move our I to next pivot?
Yeah, I said I, J. So element J in comparison with pivot, what can you say?
Sorry, I didn't get it. Maybe I need to watch.
Okay, so
J is less than pivot.
Yeah.
We should compare J with pivot.
yeah,
We have noticed that J is less than pivot, so
Yeah.
we need to swap them.
yeah,
And J now is on pivot place, so no. J is moving to I position.
yeah. So we can see that J and I not in right positions. So we can swap them, and they will be in right positions. So now we're starting our process again. So please continue.
So now we need to compare I with pivot.
Yeah,
I is less than pivot, so we swap them.
no, if I less than pivot,
If I is less than pivot,
Mhm.
we should
move I forward.
move up that.
Yeah.
I thought.
Okay. Now,
Now we compare new I with pivot.
yeah,
I is less than pivot, so we move forward.
yeah,
Now I is bigger than pivot. We should swap I to
we can like stop here,
Yes.
calculate j, and then
Pull the
yeah.
right side and compare G with I.
No. Like we have two separate operations. First of all, we need to compare I and find positions that we need to swap.
Mhm.
Then we do the same thing with j.
So now J
Yeah.
is less than pivot.
Mm-hmm.
We swap G and I.
Yeah, but you said that g is less than pivot, but 10 is
Is smaller.
yeah. So what we need to do?
We should swap G and I.
No, look. Remember, you said right thing with about I. So now we're doing the same thing with j, but like in another direction. So if j is more than pivot, it means it's in the right position.
Mhm.
And if element in right position, what we need to do with j?
We should take J to the next element.
Yeah. So move backward for j. So 0. What you can tell about 0 and pivot?
0 is less than pivot.
So is this right position for 0 or it's wrong?
No, it's not right.
So if it's not right, what we do with j?
Swap with G.
Is right?
Oh,
Yeah. So now we stop this process like we stopped it here. We're saying we found I positions that we want to swap. We found j positions that we want to swap, and now we can swap them. Okay, please move on.
So now we are on the left side.
Mm-hmm.
We should compare I with pivot.
Mm-hmm.
I is less than pivot, so we swap. We go to the right side, to the next step.
Yeah. Why?
Because we have logic that if element is less than pivot, we should go to the next element
Yeah.
until it's pivot.
Yeah, because this element in right position.
Right, like,
Yeah. So 3.
the same.
Mm-hmm.
And now we go to the right side
Mm-hmm.
because pivot is
Yeah.
small.
We stop here, and now we do our operation with j.
Compare J.
Mm-hmm.
The same thing. And now
So now I and j equal, but we need to compare j element with pivot again. So what you can say?
J is bigger than pivot.
What does it mean?
It means that it is in the right place, but I is also equal to J.
Yeah.
You are a computer, you don't think about many things simultaneously.
Yeah.
Think
Yes.
only about one counter.
So is 13 in the like you?
13 is not in the same, in the right place. So maybe we need to compare to the next element.
Like when our j like with 12.
Yes.
12 in right position because it's bigger than pivot, right?
Yes.
What you did? What did you did? You like moved j backwards, right? 13, like also bigger than pivot. What do you need to do?
Move to the left.
Yeah. 3.
3 is less than pivot.
Yeah, so we stop. Now we need to swap those elements only if I less than j. If I bigger or equal j, it means we don't need to swap them anymore. But we have one operation that we do in the end of our partition operation, partition method. What is this? Maybe you remember. So we need to, maybe someone else remember. What?
Logical last is just a method. Just a method which returns true or false.
Okay.
Okay, so maybe someone else will tell me what's the last operation in the partition method.
Well, basically, you can see this. We basically swap. Yeah, yeah. B and J. Swap it.
Yeah, so when we done with swapping I and j, and I is greater than j index, we need to swap pivot with j. And this is our final operation, and logically it means that we are moving our pivot in its destination point, because we wanted to pivot was in such position so every element in the left side were less than pivot, and we can see it here, and every element is right on the right of pivot is greater than pivot. So we did everything right.
Sorry, I have a question.
Yeah.
This, I think we said that we swap when P and I, when I is more or equal to J, but why did we move to when I is more than J?
Yeah, so this is we need to check. So we can switch I and J if I less than J, because also it's we can see logically that I needs to be less than pivot, J needs to be greater than pivot. But if I have a place that on the right side of J, it means minus and minus it's plus, you know? So I don't know how to explain it in another way, but it's we need to check this. We can't swap them if I greater than J. It's just a rule. And here, okay, if you have such helper here, we can work with this. So here you can see our first operation. It's when we check if our I element is less than our pivot. If our I element less than our pivot, we do increment of I. It's like here, but when we do such thing, it means that I will be greater, we increment in I. So we increment in I while I element is less than pivot. And this is the same operation that we did here with I. We move I while I element is less than pivot. Then the same with J, but decrement here. The same thing. And when we here, we have I and J that we want to swap. But if I greater or equal to J, we break. We do not making this swap. But if I less than J, we do swap elements of I and J. the same thing that we done there. And if we did operation break, we have one more swap. Our pivot, because our first element, so low is our first element. We swap our pivot and our J element. So that's what we did there. Is this like understandable?
If we put pivot like as a random number, for example, if we say it's not 7, it's 5.
Yeah.
Where do we put I and J? Like which elements are I and which element is J? Or we just put them in the beginning and the end itself?
It's like another interpretation of this algorithm, and in the internet you can find different interpretations of this algorithm. So you can choose pivot as a last element, as a first element, as a random element. And for example, if you have pivot that's random and you don't move it in the like not swap it with the first and last element, I think you can do like I the first element, J the last element, and just don't pass this element when you move in this direction or in another direction, for example. But it's not necessary complication, I think.
And if we, for example, put the pivot on the right side, okay, so we have I on the left and J like before this element.
Yeah.
Do we does the algorithm say the same, that if we have I here, we move it like to the right, and if the element is less, then we stop?
Yeah,
So it's
like pretty similar
it's more,
algorithm,
yeah.
but in the end we will swap our pivot not with J but with I.
Okay, I see.
Like I think that it's the
Okay.
only difference. I think. Yeah. So once more, please raise your hand who understood this algorithm. And what about you?
To be honest, not quite fully, because I guess it's one of the most complex
Yeah.
sorting methods.
Okay, so let's do another run. Can you help? So,
Okay, so we have the pivot of 0.
what?
Pivot of 0.
No, we use first element as a pivot.
So it's the pivot is going to be 3.
Mm-hmm.
And we're checking it with the next element.
So we need to define I and J.
Okay. I is 1
Mm-hmm.
and J is 0.
Okay, so you can see here we need to do operation with I. So what we need to do with I?
We need to move it, change it with the pivot.
No, we need to check.
J.
Не підказує. So we need to check. As you remember, all elements in the left side needs to be more or less in pivot. More or less.
Yeah. Okay, so we have 3, and the less will be I and J, and more will be.
More or less?
Ah. Well, less.
Less. So we need to check if our I is lesser than pivot. So is it?
It is.
Yeah. If it's lesser than pivot, it means this I element in the right position. So what we need to do next?
Compare with the next.
Yeah. So what we need to do with I?
Just leave it.
No, if this element is right, we need to find elements that's not in right position. It means we need to move I. In what direction?
Left.
Here?
On the right?
Yeah, because we don't touch pivot until the end of algorithm. So we move I here. Now, 5. More or less than pivot. Well, what does it mean?
It means that the 5 is not in the order.
Yeah, so 5 not in right position, and we want to swap it with something, right? Okay, so we like ended this part of the code, we move it to this one, and where we do manipulations with J. Okay, so in the right side of pivot, elements must be greater on or like less than pivot.
I guess greater for now.
Yeah, so we need to check element J. Is it greater or less?
It's less.
Yeah, so is this element on the right position or not?
Yes. It's right, there is a pivot.
No, it's less than pivot.
No,
pivot.
I mean, it's on the right of the pivot.
Yeah, it's on the right of the pivot, but it's less than pivot,
Yeah,
so it's
yeah.
mean
So it means that we need to move J.
no, it's not in the right position, because if element on the right position, right element, it needs to be greater than pivot.
But if we had, for example, I as 1, and we converted to 3, it was less than pivot, and we need to move I.
So regarding I, everything from I direction should be less. Regarding J, it should be greater. So
Then pivot.
then pivot.
Yeah. So
So we need to if J is greater than pivot, we need to keep it on the right.
Yeah.
Pivot.
yeah, but if it's less, what we need to do with J?
We need to move it to the left.
Right. Like your right, not right side. So 5. 5 and 5. What about them?
Pivot is greater than pivot,
Mm-hmm.
and it is J and I.
So we're not talking about I, we're talking only about J, right?
So we need to just place it like this.
What?
Just stay.
Yeah, yeah. So now we need to check if I bigger or equal to J. Is it?
Didn't we should
If we move,
zero?
move like
We will
0
not
5.
move J
Oh,
equals
yeah.
to 0.
Yeah. So yeah, 0 is not in right position because it's less than pivot. So we need to stop here. And now we need to check if I bigger or equal to J. Is it?
Yes.
Yes. So we need to swap them now. Okay. Now we need to do same thing again. Now without my help. What we do with I, then what we do with J.
So we have that 0 is less than pivot, and
Mhm.
0 is I.
Mhm.
So we need to move I to the right.
Mhm.
We had J as 5, and J is greater than pivot, so it stays like this. Oh, yeah, we need to compare J and I.
J and pivot.
Pivot. Pivot.
J and pivot. J is larger than given, so we don't need to do anything. Or move it to the left.
Yes. j and pivot one more time, because maybe here will be temp and we will move left one more time, so we need to check.
So 0 is less than 3. So
Mhm.
we don't need to move j to the left.
Yes. So now what we get?
We compare j and I.
Yes.
And j is less than I,
Mm-hmm.
so we need to swap.
Okay, let's be careful with wording. Compare j and I, or compare element on I position and element on j position. What exactly we compare? And what exactly we swap?
Elements